Hello, Fiveable. Shane coming at you for the AP Stats lesson for this week. Apologies for Thursday not being able to get this out. Was ready to go, had everything set up. The only problem was Crowdcast went down. So I wasn't able to cast for you guys, but I decided because probability is coming up in your units and in your classes that I wanted to get this out sooner rather than waiting a week. So we're going to do it Thursday night or Sunday night. How's it going, Jason? In my house, and I brought some equipment home so I could still give you the hands-on experience of actually doing the AP problems. So once again, my name is Shane, and I'll be with you all year doing the Fiveable statistics for AP Stats. We're going to start with Intro to Probability today. Lots of stuff to talk about with probability. It will take us a couple sessions to really get it down, but I promise you, you will get probability down. It's really difficult, but we'll spend some time. The other thing I want to mention is send this out to your friends. The more people we get on here, the richer discussion we have, which is going to help to better understanding of probability. I'll be doing an Instagram account in maybe a week or so and just trying to get you guys more stats stuff on a regular basis. It'll be like quick clips on multiple choice problems or how to use your calculator or free response problems, just 1-minute videos or less on how we can best use statistics. So today we're going to do Intro to Probability. As always, I'll be coming on Thursday nights, 8 p.m. Eastern Standard Time, 5 p.m. my time. Here are the next major topics. We're covering Introduction to Probability tonight. Tomorrow, probability diagrams and rules. And then the next one will be conditional probability and independence. Feel free to comment in the section on the right if you have specific questions that maybe aren't being addressed in this. Maybe you're further along. Shoot them this way, and I'll be sure to talk about them. So here's what we're going to cover today. Here's our agenda. So we're going to start with the law of large numbers, which is kind of the foundation of probability. Then we're going to get into simulation. So how do we simulate a chance process? There are a couple different ways we can do that. And on the AP exam, they're going to ask for specific simulations that you're going to want to make sure you know how to do. Then we're going to cover sample space, probability model, and what is an event. Also, just a quick pause, if Sunday nights work better for you, let me know in the comment section, and maybe I can switch from Thursday nights to Sunday nights. We're going to go over some probability rules, and then get to a multiple choice and free response question. Like I said, anytime you have a question, just go ahead and pop it into the Ask Question section. I'll be sure to help you out. Wednesday nights, all right, you can definitely make that work. So the first rule, test is always on Thursday. Okay, see, that's what I'm talking about. That feedback is very, very valuable. I'll look at my calendar and make sure Wednesdays are free, and I can switch it to Wednesday nights. But the first thing I want to let you know, Jason, and I got 2 other people in here, is probability is hard. This is something where even AP stat teachers, when we come together, it's very, very difficult to find some of these problems out. So if you're struggling, if you've been spending weeks and weeks on it, take a minute and realize, hey, this is hard and I might not get it the first time, but as I do more and more problems, it will get easier. I was just at a stat session on Saturday, helping my students with a bunch of other teachers, and we were talking about probability, and you could spend weeks and weeks on probability and students would still struggle with it. So don't worry, it is hard, and if you're struggling, that's a good sign. So the basics of probability comes down to the law of large numbers, which essentially means if we observe many, many repetitions of a chance process, the proportions of times that a specific outcome happens comes to a single value. And we have a good applet that I'm going to show you that really illustrates this. So if you do something over and over and over and over and over and over again, there's going to be a proportion of times that a specific outcome happens. It's going to approach one single value. And that's how you know what the chances of that happening are. All right, so I'm going to go to my applet here. And here it is. So how's it going, Kevin? Good to see you. Let's see if I can make this a little bit bigger. Perfect. Okay. So I'm a huge basketball fan. You can see my NBA Care shirt here. And we have this shooter who claims that he is an 80 or she is an 80% free throw shooter. So I have the line right here around 80%. So that's the proportion of makes. Percent of shots made is our Y. And then down here is the number of shots. So as I take more shots, and I'm going to take 10 shots with this person, they claim to be an 80% shooter, but we don't know exactly what they are yet. So I'm going to go ahead and take 10 shots. So there's my shots going. And look at that. I missed 9 of them and made 1 of them. So this person is clearly thinking they're an 80% shooter, but after 10 shots, not so hot. As I go, continue to take shots. Watch as it changes. So in the short term, there's a lot of variability. But as I continue to take shots, this number is going to approach the true probability of this person as a shooter. And so I'm actually going to increase this from 10 to 100, and let's see what happens. So we're taking 100 shots. If you look down here, you're going to see the shot count. And the variability is becoming less and less. We're seeing less variability as the shots. It's approaching a certain number. And that might tell us the true probability of this person as a shooter, right? So if you're Steph Curry or you're someone who's trying to get a new contract, you want to be clear about what your shooting percentage is so you can get that contract. So notice it's coming, it looks like it's about 40% of the hits versus the miss. And again, that only happens after we do this many, 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 many times. If I just do it, 10 shots, they were a 10% free throw shooter. But let's look at the true probability. So I'm going to show you the true proportion of makes that this shooter has. So it's right around 45%. And if I did this 100 more times, we would see that number, that line right there, come closer and closer to 45%. But again, that only happens in the long run after many, 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 many trials. So I would even want to get this up to maybe 300-400. And over a season, that's how you get the true percentage of a free throw shooter in the NBA, right? Over many, 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 not just one game, right? DeAndre Jordan is back in the day, I mean, he would have one game where maybe he hits all of his free throws, but that doesn't mean he was a 100% free throw shooter. If you took the whole season, then you would get a good idea of what his true makes were. So hopefully this applet, cool. What was the situation, Jason? Was it free throws as well? Yeah. And Kevin, we're going to do this on Wednesday when in our block period. I'm going to introduce this as well. So long run probability is super, super important when it comes to statistics. It's kind of like if I flip a coin, right? What's the proportion of heads that I get? Well, if I flip it 10 times, I might get 10 heads. That's not impossible. But if I did this over and over and over and over and over again, like if I did 10,000 coin flips, we would get 50% about of the proportions being heads. But you have to do it over the long term. And we're going to get to some why that is in a minute. Just like if I'm rolling a dice, right? The proportion of ones rolled, if I do this over and over and over and over and over again, is going to be 1. So you may have some, depending on what game you play as a kid, if it's a dice game, you might say like, oh man, my friend is getting really hot. They're rolling doubles all the time. But in the long run, that's going to even out, right? Maybe one game it doesn't, but if you did it over and over again, the rolls are going to even out. So here are some myths about probability. So we have the long run probability. Probability allows you to make predictions in the long run, not the short run, kind of what we talked about, right? Like if I wanted to bet on someone making a free throw, what they did in the past isn't going to allow me to predict what they do right now in the short run. But I could say, hey, DeAndre Jordan is a 45% free throw shooter, and I would bet that over the span of 100 free throws, he's probably going to make around 45. But if I said 2, you can't really make a prediction because that sample size is so small. The next one, future outcomes are not affected by past behavior. This gets a lot of people in trouble, particularly in Las Vegas. So there's a game called Craps or not craps, I should say, roulette, where there's a spinning ball or spinning wheel and you put a ball in there and it lands on red, blue, or green. Sometimes you'll see like the past 10 spins landed on red. And some people may think, hey, because the last 10 spins were red, the next one's gotta be black. And that's not the case. Future outcomes are not affected by what happened in the past. For example, if I flipped a coin, the past 10 times, let's say I flipped a heads. If I flip it now, there's no more chance of it being a tails or a heads than what it was because of the past 10, right? The past 10 do not affect what's happening right now. That gets a lot of people lose a lot of money because of that. And it's right. You feel like your instincts are telling you, hey, the past 10 were red. The next one's got to be black. Or the past 10 coin flips, like you want to feel like that's true, but that's your illogical brain talking. There's one more, I think. Yes. No, that's good. Okay. So now that we talked a little bit about probability, what we like to do as statisticians is to simulate a chance process, and we call that simulation. So it's where we take a chance behavior and we model, we create a situation that models the probability and the outcome and the situation. And we can use a couple different things for this. So we can use physical devices like a random number table, random numbers, but it's easier if we use technology. So if we use I don't have my graphing calculator, but I will use a graphing calculator on my cell phone. We can use that to simulate chance processes. And so I have a little situation here that we're going to do together. So in an attempt to increase sales for a book that I'm writing, I decided to offer a promotion. Each book will come with a collectible deck of cards featuring one of these locations as the background: Ireland, China, South Africa, Mexico, and Iceland. Each of the locations is equally likely to appear in any book. So I have this book that I'm writing. I'm not actually writing a book. This is just a situation I came up with. So I have this book that I'm writing, and in order to increase sales, I'm going to put a deck of cards in there that has a different location as the background. There are 5 different locations, and each one of those is equally likely to come up in a book. One of my students came back to me and wanted to get all 5 locations. He was surprised when I took 23 books to get the full set of locations. Should he be surprised? So this is a chance process that we're going to try and simulate to see, hey, is there something fishy going on? Like maybe this person isn't actually putting the same amount of each deck of cards in here. Or maybe Mr. Durkin, since his dad's from Ireland, is really favoring Ireland and putting a whole bunch of Ireland decks in there. So here's how we do it. And I'm going to go to my calculator. We're going to see what is the probability that it would take 23 or more books to get a full set of 5 locations. And this is where I'm going to plug. By no means do I have any stock in this calculator or this app, but if you have a iPhone, you're going to want to go to the app called Graph and Calculator 84. I know it's kind of tough to see. It's this one right here. It costs $1. At least when I bought it, it cost $1. And it does the same thing your TI-84 does, but it's on your cell phone. So I want to, ooh, this is not working. Let's see. How's that? Okay, so we want to randomly see how many decks it would take to get the full set of 5. So what we're going to do is we're going to go to math, which is right here. Then we're going to go over to probability. Now, if you have your TI in front of you, it's going to be a little bit different, the interface, but it's essentially the same thing. And then we're going to go to random int, right there, number 5. So this is where we're going to put random numbers, starting with 1, 5. And the reason we're going to do 1, 5 is because we're going to assign each deck a card to a number. So we're going to say, hey, if I get a 1, that's going to equal my book had Ireland in it. If I get a 2, that's going to indicate China got it. 3, that's going to be South Africa. If I get a 4, it's going to be, what was the other one? Iceland was one of them. And let's see, what was that last one? Mexico, that's right. Okay. If I get a 5, that's going to be Mexico. So now I'm going to hit enter, and I got 5. So I chose Mexico. I'm going to do it again. Remember, each deck is equally likely. So what I got the last time isn't going to influence what I get the next time. So we're going to hit enter again. I got 2. So now I have Mexico and China, and there are 3 left. I'm going to hit enter again because as I buy another book, I'm equally likely to have Ireland, China, South Africa, Iceland, or Mexico in that deck of cards. So I don't want to adjust anything. Enter again, 4. All right, so now I have those. Next, 4 again. So I don't have a new deck of cards. It's the same one I got last time, so I'm going to buy again. 5. Again, same thing. I already have that, so I'm going to keep buying. 1. All right, all I need is 3, and then I have the whole deck. So right now we're simulating, right, what it would be like to actually buy these decks of cards or buy these books to see what's in my deck of cards. 2, 4. We're trying to see, is 23 kind of unreasonable, right? Is it weird for me to buy 23 books to get all 5? Or is one deck favored over another? 2, 3, boom. So I got all my decks of cards. And we're going to see how many that took. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that took me 10 tries. Let's try it one more time. So we're going to go to math. You're going to go over to probability. You're going to go down to random int. You're going to put what kind of, or what's the boundary you want. So if we had 10 decks of cards, we would put 1, 10. But we only have 5, so we're going to do 1, 5. And this gives every opportunity, or gives every outcome the same opportunity. So if you had some weighted opportunities, which we'll get into when we do expected value and things like that, you would want to adjust what the probability of something coming up. But right now, each one of these 5 has the same chance of coming up, which is about 20%, since we have 5. So let's try it again. 3, 4, 2, 3, 5. All right, all I need is 1, 5, 4, 4, 1. Bam. So that actually came quicker. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that only took 9. Now we could do this over and over again, but essentially what we're going to get is 23 times is kind of fishy. Like it never took us 23 times to get all these books. So, or all these decks of cards. So I would be a little suspicious that they're actually equally dividing all the different decks of cards. I think one might be a little bit rare. So like if you've ever played the McDonald's Monopoly game, I used to love that. But there was always like one piece that I wouldn't miss or that I wouldn't have. And that's because they didn't print a lot of it. And if they did print everyone evenly, then we should see that piece just as often as the other pieces in the long run. So hopefully that helps with your calculator and how to simulate a chance process. I think on the free response, there's maybe been a handful of times when you'd have to simulate a chance process, and they'll ask you to explain it. So here we would say something like, I assign each deck a card a number between 1 and 5. Then I use a random number generator to randomly select a deck of cards. And I do this over and over and over again until I get all 5. So when you're doing the free response questions and you're talking about simulation on the AP exam, you want to talk about what you assigned to each outcome, right? So each one of these outcomes is assigned a number 1 through 5. So you got to make sure you talk about that on the AP exam, especially when you're doing simulation. All right, we're going to head back to my PowerPoint. Again, feel free to ask questions about the specific calculator about the different topics. We're going to do an AP problem in a minute to give you guys a better understanding. I think I need better lighting in my room, so we'll get that. Okay, so now we're going to get to exactly what is a sample space. Well, a sample space is a set of all possible outcomes. So it's all the different things that can occur. In a probability model, well, let me show you what a sample space is using my doc cam. So here I have 2 dice, and we're going to create a sample space together. So we're going to create a sample space of the sum of 2 die if I roll them. Right, so here are the outcomes from 1 die. I can get a 1, 2, 3, 4, 5, or 6. And here's die 2, right, my second die. Again, the only outcomes that can occur when I roll 1 die is a 1, 2, 3, 4, 5. But if I wanted to get the sum, if I wanted to create a sample space for the sum of 2 die, here's how I'm going to do it. So it is possible that if I roll a 1 here and a 1 here, it's going to give me a 2. I can roll a 2 and a 1, which gives me 3. I can also roll a 1 and a 2 to get me 3. Right, so we're creating all the different outcomes that can occur when you roll 2 die and get a sum. That's what's called a sample space. All the possible outcomes that can occur in a given situation. Here, the situation is rolling 2 die and getting the sum. So 3 and 1 would get me 4, 4 and 1 would get me 5, 6, 7, 2 and 2 gets me 4, gets me 5, gets me 6, 7, and you should see a pattern. This is 4, this is 5, 6, 7, 8, 9. This is 5, 6, 7, 8, 9. This is going to be 10. This is 6, 7, 8, 9, 10, 11. This is 7, 8, 9, 10, 11, 12. So if we're rolling 2 die, this here is called our sample space. All the different outcomes that can occur given a situation. So in this case, the situation is rolling 2 die. Now you're going to see a lot. There's a game called Craps that the whole game is based off of this probability, right? Let's go back. We're going to come back to this, but that essentially is what a sample space is. So like if you were flipping a coin, the sample space would just be heads or tails. All right, let's take a look. Again, feel free to pop, ask me questions. If this is like old school and you know this, ask me a question and I can stop and kind of tailor this to you. A probability model, so it's something that models chance process. So it's a description of a chance process that includes the sample space and the probability for each one of those possibilities, right? So we just looked at the sample space of rolling 2 die, but now we want to know, okay, what's the probability of rolling a 2, rolling a 3, rolling a 4? And so if you look on this next part right here, we have that probability. So this is that sample space that we just looked at. It's rolling 2 die and getting the sum. You're going to see down here, there's only one way to get a 2, and that's if you roll doubles. And that's a 1 out of 36 chance. Because our whole sample space was 36 possibilities, the only way you can roll a sum of 2, it's only one way. And if you get a 2 and a 2, or 1 and a 1, I'm sorry. So you're going to see that there, right? You're going to see that 2. Rolling a 3 is a little bit easier. Not much, but a little bit. By getting a 2 or 1, or a 1 or a 2. And as you can see, it gets symmetrical, and its peak is at 7. So the most likely roll when rolling doubles and rolling 2 dice and getting a sum is 7. And that's 1/6 of the time. So again, going back to craps, which is a game in Vegas, 7 is a good roll if it's not the first roll. And so that's the highest probability. But everything else, kind of goes down from there. So here is the probability that it happens. Sorry about that. Here's the probability that it happens. And here's the different outcomes that can occur. So there are 6 different ways. Let's see, 1, 2, 3, 4, 5. Yeah, 6 different ways that we can get a 7. We can get a 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. And the order doesn't matter, right? If I get a 6 and a 1 or a 1 and a 6, that's still a 7. So it still comes out to the same event, which we're going to get to right here. A collection of outcomes. So an event is a collection of outcomes from a chance process, the subset of a sample space. And we usually write it like P of A. So let's go back to my probability model right here, my sample space. So let's call the event, what's the probability of rolling an 8? And so we're going to say, let A be rolling an 8 or A8. So P represents the probability, and then we always have some sort of event there. So this is the probability of rolling an 8. So we have 36 different outcomes that can occur. Of those 36 outcomes, how many of them are 8? So we have a total of 36. Of those 36, I have 1, 2, 3, 4, 5. 5 of those 36 would get me the event A, which is rolling an 8. So that gives me the probability of rolling an 8. Now we could do this for anything, right? What's the probability of rolling a 5? 1, 2, 3, 4. Well, 4 out of 6. What's the probability of rolling a 10 or 5? 1, 2, 3, 4 plus 1, 2, 3. So the probability of rolling a 5 or a 10 is going to be 7 out of 36. Right, so the sample space really allows us to dive into the specific probabilities. And you can guarantee Vegas knows these like the back of their hands. That's how they make all their games. Right? They make it so that in the long run, they're going to win out, and they know these probabilities. All right. Now that A can change, the probability of A, the probability of B, doesn't really matter. We usually just use A and B because those are the beginning of the alphabet. There's our sample space. So here I have event A is rolling a sum of 9. What's the probability of event A happening? Well, in order for us to roll a 9, there are 4 different outcomes, right? We can get a 3, 6, a 5. I'm sorry, there's 4 different outcomes. We can get a 3, 6, we can get a 6, 3, we can get a 5, 4, or a 4, 5. So 4 out of 36 or 1 out of 9. So when rolling dice in the long run, remember, it doesn't happen in the short run, but in the long run, you're going to roll a sum of 9 1/9 of the time. So if we went back to the applet and changed it from shooting free throws to rolling die and getting a sum of 9, you would see in the beginning the proportion fluctuate. But as we did it over and over and over and over again, it would level out at about 1/9 or about 11%. So if you think about casinos, how many games they have going, hundreds of games of craps going. And so if you're rolling dice over and over and over again, they're going to get long run probability because there's so many people rolling and there's so many games going. And that's how they win, right? If you just sit down at a casino and play a game one time, that's actually your best probability. The longer you sit there, long run probability kicks in, which gives the edge to the house. But most of you guys aren't able to gamble yet, which is great. Keep your money, but if you are interested. Yeah, so that's the theoretical probability. Yeah, so the theoretical probability of rolling a sum of 9 is going to be 1/9. Again, long run. We can't predict it right off the bat, but in the long run, if you did it over and over again, it would be 1 number. Here are some basic probability rules. First, the probability of any event is always between 0 and 1. So when coaches or when teachers or when parents tell you to give 110%, that's literally impossible. The most you can give is 100%. Or if you're 100% sure of something, you are absolutely sure. You cannot be 110% sure. You cannot be 140% sure. You always have to be 100% or 0%. That means, so 100% means something is happening, 0% means it's not happening. All possible outcomes together must have probabilities whose sum exactly 1. This is going to come in big when we take a look at our free response problem, but all possible outcomes, when we add it together, their sum must be 1. So if we look back at our sample space, this thing right here, if I added the probability of getting a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I added all those probabilities together, it would be 1. So like 136 plus 236 plus 336, all the way up to 1. If all outcomes in the sample space are equally likely, the probability of an event happening can be found using this formula right here. So once again, if all outcomes in a sample space are equally likely, the probability that event A occurs can be found by using this formula. And that's the probability of A equaling the total number of outcomes that correspond to event A divided by the total number of outcomes in that sample space. So going back to this one, each one of these, because the dice aren't weighted, was equally likely to come up. So there are 36 different outcomes. So that goes on the denominator of your fraction. The top is the number of outcomes that correspond to event A. Well, in this case, event A was rolling a sum of 8. So the corresponding events or the corresponding outcomes that worked with that event were 1, 2, 3, 4, 5. So of the 36 equal outcomes, 5 of them were event A, which is what we wanted. So it's a quick, easy 5 divided by 36. You can think of flipping a coin, heads or tails. How many outcomes are there? 2. If I want to know what's the probability of getting heads, since heads and tails are equally likely to occur, I take the number of outcomes possible, which is 2, and then on top, put what I want, which is 1. There's one way I can get a heads, and that's by getting a heads. Fourth rule, probability of an event does not occur is 1 minus the probability that it does occur. So let's go back to this. The probability that I roll an 8 is 5 out of 36. The probability that I do not roll an 8 is 1 minus the probability that I do roll an 8. So it's 1 minus the probability that I do roll an 8. Well, 5 out of 36 is how if I roll an 8. So I could do 1 minus 5 out of 36. And that would get me the probability that I do not roll an 8. That's called the complement rule. We're going to look at that when we do our practice problem. One more. If 2 events have no outcomes in common, the probability that one or the other is the sum of their individual probabilities. So going back to this. If 2 events have no outcomes in common, like I cannot roll a 2 and an 8 at the same time. So because of that, if I wanted to figure out the probability that either one occurs, I could just add them together. So for example, the probability that 8 occurs is 1, 2, 3, 4, 5. The probability that 2 occurs is 1. And because there's no overlap, I could just add 1/36 to 5/36 and get the probability of rolling an 8 or a 2, which would be 6 out of 36. And lastly, 2 events are considered mutually exclusive. Some textbooks use disjoint, so I'm going to put disjoint in there too. If they have no outcomes in common and so can never occur together. So once again, 2 events are mutually exclusive or disjoint if they have no outcomes in common and so can never occur together. So for example, I can't roll simultaneously a 2 and an 8. Those are mutually exclusive. If I roll 2 dice, I'm getting one number, I can't get 2. Okay, so let's take a minute and look at this free response question. Airlines routinely overbook flights because they expect a certain number of no-shows. And we actually recently saw this in some, I think Delta Airlines had a big instance about this maybe a couple months ago or a year ago. An airline runs a 5 p.m. commuter flight from DC to New York on a plane that holds 38 passengers. Past experience has shown that if 41 tickets are sold for the flight, then the probability distribution for the number who actually show up are in the table below. So, looking at our table below, 36 people show up for the flight if they sell 41 tickets 46% of the time. 37 people actually show up for the flight 30% of the time. 38, 16, 39, 5%, 42%, 41, 1%. So notice if I added all those probabilities together, they should add what? 1. They should equal 1 if I add up all those probabilities together, and they do. The other thing is mutually exclusive. So the number of people who show up, can I have 36 people show up and 39 people show up? You can't. You either have one or the other. So because of that, these two events, an event being the number of people showing up 36 or the number of people showing up 39, those two events can't happen at the same time. So they're what we call mutually exclusive. Right? So it's kind of like you can't be in two places at once. I can't be enrolled in first period AP Stat and first period Calculus. Those two are mutually exclusive. Now, if it's a different period, then they're not mutually exclusive. But you can't be enrolled in AP Stat and AP Calculus during the same period. Those are mutually exclusive. Just like right here, we can't have 36 people show up and have 37 people show up. They're mutually exclusive. Okay, so assume that 41 tickets are sold for each flight. There are 38 passenger seats on the flight. What's the probability that all passengers who show up for this flight will get a seat? So I kind of made that probability distribution right here. So this is the number of people who show up for the flight. This is the probability that it happens. So remember, all these added up should be 1, and it is. And if we want to know what's the probability of event A happening, we want to know what's the probability that all people who show up for the flight get a seat. Well, this holds 38 people. So if 36 people show up, will they get a seat on the flight? Will everyone get a seat on the flight? The answer is yes, they will. So we want to add the probability that 36 people show up plus, well, if 37 people show up, they will also get a seat on the plane. So that's plus the probability that 37 people show up. If 38 people show up, all of them will get tickets, or seats, I should say. So 38 people will also get tickets. And those are the only outcomes in our sample space. So our sample space is 36, 37, 38, 39, 41. Those are all the different outcomes that can occur for this. Of those outcomes, the ones that work for us, or the ones that allow event A to happen, are going to be 36, 37, 38. And because those are mutually exclusive, we can add them all together to get the probability that event A happens. So the probability that 36 people show up is 46. The probability that 37 people show up is 30. The probability that 38 people show up is 16. And if you add those two, all three together, you'll get the probability that all passengers who show up get a seat. And that's going to be 92%. So the probability that everyone who shows up gets a flight or gets a seat is 92%. Now that's a pretty high probability, which is why they oversell. Because let's say some people, let's say 40, 39, 41 people show up. That's a low probability. And the money they make, airlines make from overselling tickets and having people no-show will cover what they would then have to pay people to say, hey, we don't have enough seats on this flight. Can we pay you $500 and put you on a flight later? So they work out that math, right? They're looking at the numbers. They're looking at the probabilities that, hey, if we sell 41 tickets, here's the probability that everyone gets a flight, or here's the probability that no one gets on the plane, or 2 people don't get on the plane. What's that difference? And then how do we make sure that we sell our ticket prices at a rate that will allow us to make money? So let's go back to the complement rule for this problem, because there's another way we could have solved this. Event A was the probability that all passengers who showed up for this flight get a seat. We could find this by finding the probability that some people won't get a seat on the flight. Probability of B happening. So we could do 1 minus the probability of B happening to get the probability of A happening. That's the complement rule, right? So the probability of B is that people who show up don't get a seat on the flight. Well, that happens when 39 people show up, plus 40 people showing up, plus 41 people showing up. So if I did 1 minus all these added together, I would get the probability that A happens. So 1 minus, probability of 39 happening is 0.05, plus the probability of 40 people showing up is 0.02, plus the probability of 41 people showing up is 0.01. All that is 0.08. 1 minus 0.08 gives me 0.92. So there's the complement rule in action on one of the AP stat free response questions. That's just a very, very quick introduction to probability. We're going to dive more into it as the week continues. And again, I will be doing an Instagram page to help you guys with stats, and it'll just be like 1-minute videos of maybe breaking down what a sample space is, or maybe breaking down what a probability distribution is. Just different ways to keep you guys engaged and keep you guys helping you guys out throughout the process of this AP exam. I'm looking for I'll tell you guys the handle when I get it, but for right now, it's just all up here, and I'll get it down on paper. Probability is tough. We'll dive more into it on Thursday when we get into like tree diagrams and Venn diagrams, different ways that will help us with probability. But that's just kind of the basics of probability now. We'll dive into it more on Thursday. Well, stick around if you have any questions, but that's it for me tonight. It's weird doing it on Sunday. Kind of like it, but I definitely need to get the lighting better in here. So Jason or Kevin, if you have any questions, please, please, please let me know. All right. If not, it's been fun. I will see you guys on Thursday for our next session of Fiveable, looking at tree diagrams and Venn diagrams in different ways that will help us with probability. All right, Kevin. See ya.